The foundation of computing happens at a very macroscopic level. We take a Snapdragon from a Samsung and we zoom into it. It reveals millions of transistors, but it is very difficult to actually pick apart these transistors. To understand it, we have to treat transistors like Lego blocks. And in this video, we will be talking specifically about a 1x2 Lego brick called a CMOS. Our presentation titled CMOS Review, Hun Seng, Amar and I will be talking about the CMOS technology. First, we'll be talking about a brief introduction, a look at the 3D structure, the layers that make it up, and also the fabrication process. Let's get started. Also known as the metal oxide semiconductor, it is a piece of technology that is modern in modern integrated circuits. CMOS in its name is actually complementary because it combines two pieces of Lego bricks called the N-type and P-type MOSFETs. As of 2011, 99% of IC chips were fabricated including digital, analog and mixed signals using CMOS technology. The simplest application of CMOS technology is actually in this simple circuit here called a CMOS inverter. It acts like a NOT gate where when you put 1 inside it, the output will be 0. This happens because when a gate voltage is applied, aka at the input, the NMOS is biased while the PMOS is unbiased, causing the ground to short to the output, yielding a 0, and vice versa happens when no gate voltage is applied. Many processes that were developed to fabricate the CMOS, the twin well silicon gate process, which is discussed in this video, the N well process, the P well process, and the triple well process also with the gate technology. The industries that use CMOS technology are far and wide. Here, we have digital electronics and consumer electronics, communication systems, industrial and IoT, and also medical devices. Next, we look at the 3D structure of a CMOS. Here shown is actually a CMOS that is produced by twin-well silicon gate process, which is the one that we'll be talking about today. Physically, we can actually see the complementary nature of the CMOS. Here we can see in the blue and the yellow, a P well and an N well that is implanted on the same substrate. Next, what we can see in this structure is also the fundamentals of a basic transistor. You can roughly make out that there is a drain, a source and a gate, which is shown in this area. You can also look above and see the metal interconnects that connect these things. It may vary based on how you want the CMOS to behave, but if you want to look at the logic gate earlier, we look at the CMOS inverter, right? The gate would have to be shorted, the PMOS drain and the NMOS source would have to be shorted, while the drain and other connections go to either a ground or the source. So we can see that from this very basic structure, these things is what makes the fundamental block of a CMOS. To summarize, this structure is the fundamental building block of a CMOS. How industries use them is actually varying how they use the metal interconnects, but how you get those drains, how you get those gates is actually dependent on the process itself. It is mainly used to vary logic gate behavior, and arranging these specific arrays of logic gates is actually what allows us to do computing.
Next, we'll move on to the CMOS layers, which are the fundamental physical layers used to build a CMOS integrated circuit. Each layer plays a different role, from forming the transistors themselves to connecting and protecting the entire chip. We'll start from the base, the substrate. It's a thin slice of silicon, usually P-type, acting as the foundation for all other layers. On top of it, a thin oxide layer is grown through thermal oxidation. This oxide works as an insulator, protecting the surface and preparing it for further processing. Next, we define the N-well and P-well regions. Through a process called doping, we implant impurities to change the conductivity of specific regions. The N-well is where we will build the PMOS transistor, while the P-well is for the NMOS transistor. This step allows both transistor types to exist side by side. This complementary structure allows CMOS to achieve low power consumption while maintaining high performance. Next, we form the gate structure, which controls how the transistor switches. First, a very thin gate oxide is grown to act as insulation. Then, a layer of polysilicon or metal is deposited and patterned to form the gate electrode. The gate controls the current flow beneath it, turning the transistor on or off depending on the input voltage. Next, we create the source and drain regions on both sides of the gate. These are formed through ion implantation, with the gate serving as a mask to ensure perfect alignment. A heating process called annealing follows, which activates the dopants and repairs the silicon crystal. This completes the basic structure of the transistor. Once the transistors are ready, we need to connect them together using metal layers. These layers, typically made from aluminum or copper, form the horizontal wiring lines on the chip. Each layer routes electrical signals across the circuit, linking transistors into logic gates and functional blocks. Between each metal layer, we deposit an interlayer dielectric, usually made from silicon dioxide or other insulating materials. The dielectric prevents short circuits between metal layers and maintains electrical isolation. It also provides mechanical support, ensuring each layer remains stable during fabrication. As for the contact and wires, to connect different layers vertically, contacts and wires are created by etching small holes through the dielectric. These are filled with tungsten or other conductive metals to form pathways for current between the metal layers and transistor region. Finally, for the last layer, the passivation layer is deposited over the entire wafer. It serves as a protective coating, shielding the chip from moisture contamination and physical damage. Only the bonding pads areas are exposed, allowing external electrical connections.
Now, before we can get into the steps required to create a twin-well CMOS, it is important to know 9 of the most common processes involved in fabricating any modern IC. The first of which is oxidation. This simply involves growing a thin silicon dioxide layer above the substrate and is usually done in a high-temperature furnace. The next process, photolithography, is when the design of the IC is transferred onto silicon. The substrate is first coated with a layer of photoresist and then exposed to UV radiation through a mask. This mask or reticle is what provides the specific pattern for a certain layer of the chip. UV exposure either softens or hardens the photoresist over regions where it is to be kept or removed during the etch step. During etch, the soluble regions of the photoresist are removed either through chemicals or with ionized gases, which exposes the layer below them. In modern fabrication, thermal diffusion and ion implantation are 2 different processes used to dope a substrate. In diffusion, gaseous dopants diffuse into exposed regions of the substrate at high temperatures, whereas in implantation, these dopant ions are directly accelerated via an electric field into the silicon substrate. Ion implantation is much more accurate and can be done at room temperature and is able to implant ions through a thin layer of oxide. However, annealing has to be done to repair the crystal structure after implantation. Chemical vapor deposition and physical vapor deposition are 2 processes that are used to deposit a solid material onto the substrate. In CVD, volatile chemicals react or decompose onto the surface of the substrate. In PVD, however, the material to be deposited is hit by high-speed ions, which causes it to vaporize and afterwards condense onto the substrate. The last 2 general steps are CMP and clean. CMP involves the use of chemical and mechanical forces to planarize and flatten the surface of the wafer, after which the clean step is done to remove contaminants or byproducts left over. This is also usually done after etch and photolithography. With the general fabrication steps out of the way, we can now move on to the steps required to fabricate a twin-well CMOS. First, the N-well and P-well are created. In doing so, a thin oxide layer is first grown on the surface of the substrate. Then through photolithography, the region for the N-well is defined, which afterwards is implanted with N-type dopant. In creating the P-well, similar steps are performed. The wafer then undergoes high temperature drive-in to diffuse the dopants into the substrate and to anneal the crystal structure. After both the N-well and P-well have been created, the thin oxide layer is removed and replaced with a new thin pad oxide layer along with a layer of silicon nitride. The next step is the definition of the shallow trench isolation and transistor sites. The regions for the NMOS and PMOS are known as active area and are patterned and developed such that a trench can be etched between them. An oxide is then grown and deposited across the wafer to fill these trenches. After that, the wafer is planarized through CMP until just above the nitride layer. With the transistor sites defined, the next step in fabricating a twin-well CMOS is the definition of the drain, source and gate regions. Field implants of N-type and P-type are first done. Then the nitride layer is removed and replaced with a thin layer of gate oxide. Polysilicon, which will be the material for the gates of the transistors, is deposited, patterned and etched accordingly. The source and drain of both PMOS and NMOS undergo lightly doped implantation, which later minimizes the impact of ionization. After the gates of the transistors are defined, nitride spacers are formed on the sides through the deposition and anisotropic etch of a thin nitride layer. Once the nitride spacers have formed, the source and drain regions for both NMOS and PMOS can be patterned and developed, where N-type dopants and P-type dopants are implanted for the NMOS and PMOS respectively. The wafer then undergoes annealing to activate the implanted ions. Before the contacts for the CMOS can be made, the wafer first undergoes salicidation. In this step, titanium is sputtered and deposited across the entire wafer. Annealing is done to cause titanium silicide to form at all silicon interfaces. The excess titanium is then removed through etching. In the formation of the contacts, a thick oxide layer is first deposited and planarized. The regions where the contacts will be are patterned and defined. The oxide at these sites is etched until the surface of the silicide layer is. In the formation of the contacts, a thick oxide layer is first deposited and planarized. The regions where the contacts will be are patterned and defined. The oxide at these sites is etched until the surface of the silicide layer is reached. A layer of titanium nitride and a layer of thick tungsten is then deposited. The surface of the wafer is flattened afterwards until only tungsten plugs remain. After the contacts are formed, the remaining steps left in fabricating the twin-well CMOS would be to form the metal interconnects and vias. An interlayer dielectric and aluminium are deposited to form the M1 layer. The interconnects are defined where regions of excess aluminium are etched away. The steps involved in creating the metal vias is similar to that of the contacts. An interlayer oxide is deposited with the via regions defined through etching. A thin layer of titanium followed by a thick layer of tungsten is deposited to fill the vias. The wafer is then planarized until only tungsten plugs remain. The same steps for interconnects and vias are repeated for as many metal layers as required, according to the design of the IC. After the last metal layer, a passivation layer is applied on the wafer surface and removed where pad regions are defined. And with this, we have successfully fabricated a twin-well CMOS.
That concludes our video. Feel free to learn more about the twin-well CMOS by checking our 3D structure on Sketchfab. It was made in Blender by me. Scan the QR code or click the link in the description.